Hello friends, welcome to the first installation of a Limits and L'Hopital series. In this series, we are going to find certain exotic limits without using the L'Hopital's rule. And it's a conservative approach to limits. We shall be only using basic algebra, generalized binomial theorem, at most a bit of series expansion, that's all. Here in this episode, we explore determining limits and L'Hopital rule of the following limits. The first limit looks very much algebraic, quadratic. Limit x goes to infinity, x square plus 2x plus 3 power 1 by 2 minus x square plus 3 power 1 by 2 power x. Oh, that power sounds exotic. Second limit is limit goes to 0, limit p goes to 0, pi by 2p multiplied by 1 plus e power minus 2 pi p divided by 1 minus e power minus 2 pi p minus 1 by 2p square. Okay, that limit seems very nice, a bit difficult to evaluate, but we shall see that it is not at all. Third one looks almost impossible. Limit n goes to infinity, n factorial divided by n power n whole power 1 by n. Okay, we shall see how we can evaluate these limits in this episode. So why we believe the L'Hopital's rule is evil? The rule is mechanical and don't let you into any insight. And that's the foremost reason that we avoid L'Hopital's rule as much as possible. And in 99% of cases, you can get away without using it. Okay, in 1%, we should not do that. Often it unnecessarily complicates the process. So you could have seen it in some other YouTubers limit evaluation using L'Hopital rule episodes. And in my opinion, they are unnecessarily complicating the limit evaluation process by artificially using L'Hopital's rule without much need. And the third point is it is useless for certain expressions where you can't make any progress even after applying umpteen times. So there are certain examples that if you apply the L'Hopital's rule again and again, you will not be getting anywhere. And think about the situation where you have exponential functions upstairs and downstairs evaluating to 0 or infinity, something like that. And as you well know, the exponential function won't budge for differentiation. It would remain the same after even after applying a lot of times the differentiation. So last but not the least is that it was fought for money by L'Hopital from John Bernoulli. Bernoulli, I think he sold his finding for case to L'Hopital, who was a lad in medieval times. If you don't believe it, you can have a look at Wikipedia page describing this thing. It's a bit clear. So with these few words of blindfoldly applying the L'Hopital's rule, let us proceed to find the limit of our first problem. Limit x goes to infinity, x square plus 2x plus 3 whole power of minus x square plus 3 whole power of whole power x. And that whole power x sounds familiar in the sense that if we have x, some function of x power x, you can expect it has something to do with the exponential function. We shall see it at last. So now we just write it, limit to x goes to infinity, blah 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 blah. And in the second step, we do one thing that's seems almost unnecessary. We just break the 3 in the first term into two parts, 1 plus 2. So we have x square plus 2x plus 1 plus 2 whole power of minus x square plus 3 whole power of whole power x. And the reason that we broke 3 into 2 parts is that we are going to complete the square, a process, the ancient process discovered by Indian mathematicians, is that completing the square in solving quadratic equation. So we have completed the square. We have written x square plus 2x plus 1 as x plus 1 whole square. That's all. It is the only difference. And now we have taken out x square from that x plus 1 whole square. So we have x square within bracket x square 1 plus 1 by x whole square plus 2 whole power 1 by 2. So, okay, and that's the same thing as before. Now we apply generalized binomial theorem that says that for x that goes to 0, 1 plus x whole power n, where n is a rational number, is given by 1 plus power, that power multiplied by n multiplied by x. Here in the place of x we have 1 by x. As x goes to infinity, 1 by x goes to 0. So we can apply generalized binomial theorem in this case. So we have 1 plus 1 by x whole square is equal to, almost equal to 1 plus 2 by x in the limit x goes to infinity. And we have multiplied in the second step, we have multiplied x square into the bracket of the first term, and x square plus x square multiplied by 2 by x plus 2 whole power 1 by 2 in the first term we have. So now we cancel x with x square in the second term of the first step within the bracket, and so we have x square plus 2x plus 2 whole power 1 by 2 as the first term. That's magic. We have transformed x square plus 2x plus 3 into x square plus 2x plus 2. So to you that sounds a bit suspicious, but I promise you that's a valid step. We have just used generalized binomial theorem and magically transformed x square plus 2x plus 3 into x square plus 2x plus 2. Oh, that's magic. So now we take out x square from the whole of the first term. X square, we after taken out, that becomes x square bracket 1 plus do x by x square plus 2 by x square whole power 1 by 2. So also we have transformed the second term as after taking out x square bracket 1 plus 3 by x square whole power 1 by 2. So that's valid. So now we apply the power 1 by 2, the square root to individual factors of each term, and we have in the first term x square whole power 1 by 2, 1 plus 2x by x square plus 2 by x square whole power 1 by 2 minus x square whole power 1 by 2 multiplied by 1 plus 3 by x square whole power 1 by 2 whole power x. So the square bracket, the greater thing, whole power x, we should not forget it. It is there aptly. Okay. So now, after some cancellations, of course, x square, square root of x square is x. After some cancellations, we have within the bracket of the first term 1 plus 1 by 2, 2x by x square plus 1 by 2 multiplied by 2x square. We have just applied generalized binomial theorem again. So we have applied the generalized binomial theorem again. That's due to the great Newton who generalized the binomial theorem, Sir Isaac Newton. Salute, sir. Minus x multiplied by 1 plus 1 by 2, 3 by x square, whole power x. Okay. So now we have we are going to multiply x into each term. So after multiplying, that becomes x plus x by 2 multiplied by 2x by x square plus x by 2 multiplied by 2x square minus x plus x by 2 multiplied by 3 by x square whole power x. So now we are in a position to cancel the terms. We just apply minus sign into the second term. After applying, we have x plus x by 2, 2x by x square plus x by 2 multiplied by 2 by x square minus x by 2 multiplied by 3 by x square. Okay. So now we have cancelled certain terms. So you can see here. So we have cancelled that x term. So now we have x by 2 multiplied by 2x by x square plus x by 2 multiplied by 2 by x square minus x by 2 multiplied by 3 by x square whole power x. So after a certain cancellation, that becomes 1 plus 1 by x minus 3 by 2 1 by x. We can take that 1 by x out of those two terms, last two terms, and after taking out, it becomes 1 plus limit x goes to infinity 1 plus 1 by x 1 minus 3 by 2 whole power x. So now we have written that equation as limit x goes to infinity 1 plus, in the numerator we have minus 1 by 2 over x whole power x. So if you remember the definition for exponential function due to Euler, who introduced this nice definition, exponential x, that means e power x, is given by limit n goes to infinity 1 plus x power, x over n whole power n. So that means that in place of x, we have minus 1 by 2 in the limit, and in place of x we have n. So that just becomes e power minus 1 by 2. Oh, that's 1 by square root of 2. That's a nice result. So now we are going to have a look at the limit of the general form. Limit x goes to infinity, ax square plus bx plus c whole power 1 by 2 minus ax square plus c whole power 1 by 2. A, B, C are coefficients and the constant terms in the quadratic equation. Essentially, after repeating the same steps that we have just dealt with for a specific example, we arrive at limit x goes to infinity p by 2 root a whole power x multiplied by e power minus p by 4a. That's great. If p is equal to 2 root a, the limit, our limit becomes as p over 2 root a is 1, 1 power x goes to infinity is 1. We just have e power minus p by 4a. That's nice. But if we greater than 2 root a, the series diverges to, the limit diverges to infinity. The reason is that within square bracket of the first factor p by root 2 root a is greater than 1, and greater than 1 whole power x goes to infinity is certainly okay. You can get a test of it through your calculator. Would just diverge to infinity. If p less than 2 root a, then the case will be the series would converge, but converge trivially to 0. The limit would converge trivially to 0. Okay, that's our flock, the flock of our great country. So I have provided an indirect Desmos plot, and you can get to it through the link provided in the description. So second limit is a special limit. In what way it is special, we shall see presently. The trick is to expand the exponential function e power minus 2 pi p only up to third order, and we neglect other terms of higher order. The reason is that we need to keep the numerator and denominator homogeneous. That means they should have same order of expansion. So if you look at the denominator, it has p square, and if I expand the other factor in the denominator of the first term, 1 minus, that is 1 minus e power minus 2 pi p, then it would also become 2 pi p minus 2 plus 2 pi p. So p square multiplied by p cube, it would become p cube. So I'm going to keep terms, the powers of p only up to the third degree. Okay. Also, if you look carefully, we have multiplied the second term of the equation downstairs and upstairs by 1 minus e power minus 2 pi p in order to make the denominators of those two terms same, so that we can do algebra easily. Okay. So I have just expanded the exponential series. If you remember exponential series, e power x is given by 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, and so on. So as I already told you, we expand only up to the third power of p. So okay, that's all. We expanded the series. So now we apply the plus and minus within brackets upstairs and downstairs. 1 plus 1 plus minus 2 pi p 2 pi p whole power 1 by 1 factorial 1 minus 2 pi p whole square by 2 plus 2 pi p minus 2 pi p cube by 6. 6 comes from 3 factorial, 3 multiplied by 2 multiplied by 1. That's okay. So I have worked out those factorials. Sorry. So again, we multiplied by pi p in the numerator. 2p square remains in the denominator the same. We have not yet multiplied by it. So again, a very simple algebra. Pi p plus pi p plus pi p multiplied by minus 2 pi p whole power 1 by 1 plus so on so. It is a very simple algebra. You can have a look at it. If you have doubts, you can ask me in the comments section. It's simply basic algebra, that's all we are doing. So finally we have got there after certain cancellations. So the final limit, there is, okay, I have to tell you one thing. Okay, I am keeping up only the terms up to the third power. The final result is 12 pi cube p cube by 6 minus 8 pi cube p cube by 6 after some simple algebra over 4 pi p cube. Finally, there, a very special limit indeed. The limit distills as 5 square by 6. It doesn't contain any p there, so that is a limit. And the Basel limit too, since you might all well remember, that was the result of a series that was solved by the great Euler. 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square plus so and so 5 square by 6. That's a very Basel limit. A challenge posed as a challenge to the mathematicians then. It was solved by Euler, the great Euler. Nice limit. So I have provided an interactive Desmos plot, and the link is given in the description. So limit 3, is this a monster? So when I was browsing somebody else's YouTube videos, I have seen in the comment section after the guy, the YouTube math guy worked out the limit for the quadratic equation that we have seen as the first example. Somebody called Canis Polychronopoulos, multiple time polychrono, that's the meaning of it. I don't know what is the meaning of Paulo. Commented that while I have to admit it was quite a daring and time consuming methodology wise, it was pretty simple. That the quadratic limit, if you remember, that was pretty simple, not even comparable to some monster like limit n factorial by n caret 1 by n. That means n factorial by n power n whole power 1 by n, with n approaching infinity. That is by far the most difficult one I have ever seen, he commented. When I first saw this comment, I could not help myself smiling. As a physicist, I well know the limit is simply 1 over e, the reciprocal of Euler's constant. E. So the reason is that all physicists are acquainted with Stirling approximation. It's just a child, a phone for physicist. A physicist can immediately see the limit of this, no need to compute explicitly. The magic lies in the Stirling approximation for large n. Stirling approximation gives you a functional expansion for n factorial. Natural logarithm of n factorial is approximately equal to n ln n minus n. So after a few very easy transformations, it becomes n factorial is approximately equals to n power n e power minus n. And now if we substitute this n factorial is equal to n power n e power minus n in the original limit, we have n power n e power minus n divided by n power n whole power 1 by n, limit n goes to infinity. Oh, that just distills to e power minus n by n, and that is simply e power minus 1, and that's 1 by e. Again, Euler's constant, reciprocal of Euler again. hero. An interactive Desmos plot. I have provided in the description a link to it. You can play with it. Also, here is some nice exercise for you. You can prove that using the same steps that we have carried on in carrying out the limit of the first example we have seen. 1 by pi square x square plus 2 by pi x plus 1 whole power of minus 1 by pi square x square plus 1 whole power of whole power x limit x goes to infinity is equal to I for I, whereas I is the imaginary root of minus 1. I don't see anything imaginary in it. It's just as natural numbers to me. Of course, it's only axiomatic. Everything in mathematics is axiomatic just as well. And you can check it through Desmos. Of course, you have to take the ith power of I. You can easily do it. I hope you can do it. Easily do it. So also the second exercise is a very trivial one. It is comma 1 plus x by x power x whole power 1 by x as limit x goes to infinity. You have to find it. It's a very trivial one. So don't miss. In a future episode, we shall derive a generalized binomial theorem in a way you can explain it to your granny in an oncoming episode. Okay. Of course, your granny should not be a retired math professor. Okay. Here is the quote of the episode. The most beautiful thing we can experience is the mysterious, as you could have experienced at seeing I power I as a limit. It is the source of all true art and science. Yes, it is the feeling that you are dealing with something mysterious, something unknown, and you are striving towards knowing it. Is the driving force behind all true art and science, as have been copied by the great Einstein. Please subscribe and don't forget to click bell icon for more updates.